Everybody, I'm going to talk about degrees of unsaturation in this video. So for degrees of unsaturation, we're really asking ourselves how many pi bonds and rings are present in a given molecule. So if you're here, somebody's talking about an unsaturated molecule versus a saturated molecule, that saturation amount they're talking about is really the amount of hydrogens that can be bonded to carbons, okay? So if I have a pi bond or a ring, I'm going to have a situation where I am unsaturated in that I could have had more bonds to hydrogen, but instead I've got more bonds to carbons, okay? So we're looking at the maximum number of bonds to H in the saturated case. So if I'm looking at just hexane down here, we have no rings, we have no pi bonds, we have a formula of C6H14, okay? And you can kind of think about that in that if we just have a straight chain, we're going to have two H's on any of the internal carbons, which is a total of 8. We have 2 on the end carbons, right, which is an additional 12. But then to fill out that octet on our kind of terminal end carbons, we have to add another H each. So in the saturated formula, we're really looking at the number of hydrogens can be determined based on the number of carbons, where that saturated formula is going to be 2n plus 2 for the number of hydrogens when n equals the number of carbons. Okay, so if I had something like 7 carbons, I would have 2 times 7 plus the additional 2 on the ends, and we'd end up with 16 hydrogens in a saturated case. Okay, if we look at this alkene, so I still have 6 carbons, but now I have added in a pi bond, and by doing so, I have taken away 2 hydrogens, right? So I've taken away 2 bonds to hydrogen, so now I'm at C6H12, okay? Again, if we look at another example of C6H12, this is in the ring form, and again, we have taken away 2 hydrogens to enable us to form that ring, right? Then we look at another C6 option. This is C6H6. And we look over here and we see that we've got a ring. We also have 3 total pi bonds, okay? So if I'm looking at this, each instance of a ring or a pi bond is going to be 1 degree of unsaturation. So over here we have 0 degrees of unsaturation. Here we have 1. Here again we have another 1. And over here in the case of benzene, we have 4. Okay, so when you're just looking at them visually, you can identify that pretty quickly by just counting out, the number of pi bonds, the number of rings, adding all that up together for your degrees of unsaturation. But a lot of times you'll be given a formula and it will ask you to draw a structure that matches that formula. And it's really, really helpful to have the idea of, well, how many rings should I be drawing? Or how many pi bonds should I be drawing? Should I be drawing any of those? That's a really helpful tool to use when you're kind of putting forward some ideas for possible isomers that match that formula. So again, remember we've got our saturated formula is 2n plus 2. And notice what happened every single time we added 1 degree of unsaturation. We have lost 2 hydrogens, right? When we have 4, we ended up getting rid of 8, right? So it's 2 per degree of unsaturation. So each degree of unsaturation takes 2 hydrogen spots. Okay, where we used to have hydrogens, but now we do not. So there's kind of 2 methods of going about how to calculate this number when you are only given the formula and not a structure in front of you. The first option is a memorization option. This is one that I have never been able to memorize this formula. The only thing you need to know in terms of how to use it is just that is your number of carbons, that's your number of nitrogen atoms, number of hydrogens, and the number of halogens. So this is going to be like bromine, chlorine, iodine. Any of those are going to be your X. But I have never been able to memorize this. So what I do is I kind of do something that allows me to be able to just kind of remember, well, I actually don't remember much, but to use my knowledge of structure to be able to allow me to figure out the degrees of unsaturation using a much more simplified formula, where I'm really looking at this and saying a degree of unsaturation is the difference between the number of H's that I would have in a saturated case, right? So like if we look at this saturated case, minus the number of actual hydrogens that I have, and all that divided by 2, because again, it takes magic number of 2 hydrogen spots to do any degree of unsaturation, okay? So if I'm looking at C6H12 here, actually, let's go ahead and do the C6H6. So for example, if we're doing C6H6, I would first calculate how many hydrogens I would have in the saturated case. So I would have 2 times 6 plus 2 for my saturated case, which is 14. Subtract the actual that I have, which is 6, and divide all that by 2. So 14 minus 6 is 8, divided by 2 is 4. Okay, so that's 4 degrees of unsaturation. So that's a case where I kind of know this one because I know that, it takes 2 each of 2 hydrogens from the saturated case to make it unsaturated. So that's really what I'm aiming for here, is then I can just kind of remember that, and that's much easier for me to remember than this one. But if this works for you, go for it. You just do whatever is going to work for you. So the thing that we have to keep in mind here is that if there are other atoms present, we need to make sure that we are taking those into account. So if we have other atoms present, the most common ones you're going to run into is halogens, oxygen, and nitrogen. Okay, so the nice thing is you can just draw up a structure. If you can draw a structure that includes some of those atoms, you can essentially derive how this all works just by visualization, because you can draw up one and then just check it yourself. So if you can draw one up, and we're looking at this and saying, well, that has still 4 degrees of unsaturation between the 1 ring and the 3 pi bonds. So my degrees of unsaturation has to equal 4, but this would also be exactly the same as if I just had benzene, right? If I just had H and H instead. So that's really what we're doing here, is we're just doing whatever modification needs to occur to make it match benzene. Okay, or whatever structure that you have drawn that looks similar to something that you can identify the degree of unsaturation with. So if I've got C6H4Cl-Br, I need to get that looking like C6H6. Okay, to make that happen, I'm going to add 1 H per X. Okay, so at the end of the day, I'm really using that to do my degrees of unsaturation calculation from. Okay, where again, we would do the same, 14 minus 6 divided by 2 equals 4. Okay, so if you have any halogens, just add an H for each of those X's. Okay, so we're just adding an H for every X. All right, so then let's look at what happens if we have oxygen. So again, oxygen, I put it onto a benzene ring. I added an H on it just so that everything is nice and neutral. So I have a ring and my 3 pi bonds. So I still have 4 degrees of unsaturation here. And if I'm looking at this, if I just kind of cross out that O, I already have it there, right? I already have the C6H6 that I would expect. So in this case, we're just going to take that C6H6O and just think about it as if it's just C6H6. Okay, so then we can again do the 14 minus 6 divided by 2 equals 4. So whenever you have an oxygen in a formula, you can just go ahead and ignore it. Okay, you don't have to do anything about it. You just go ahead and calculate using your carbons and your hydrogens. All right, so nitrogen is kind of the tricky one here. So I've got C5H5N. And again, we're looking at this as we got a ring, we have 3 pi bonds, so we still have 4 degrees of unsaturation here. So I still need to get this looking like C6H6. Okay, because if I am able to get this looking as a C6H6 does, I'm going to be able to calculate it to the same thing, and then you can apply this rule onto whatever else you're trying to do. So to do that, I need to add 1 C and 1 H, right? So essentially what we're looking at here is that this nitrogen is taking the place of a carbon and a hydrogen. So we're going to take away the nitrogen and we're going to add 1 carbon and 1 hydrogen so that we can again do our 14 minus 6 divided by 2 equals 4. Okay, so if you've got anything with a nitrogen in it, you're going to add 1 carbon and 1 hydrogen for each nitrogen. Okay, so let's look at some examples here real quick. So if I've got C6H8O and I want to calculate the degrees of unsaturation, I can just go ahead and ignore the oxygen and say that I've got 2 times 6 plus 2. That's going to be my saturated number, right? So that's 14. Subtract my actual number, divide that by 2. So 14 minus 8 is 6, divided by 2 is 3. Okay, so again, we're just ignoring oxygen. Okay, we can just use the C6H8. Okay, so we're really calculating from just that simplified one. All right, so if we've got C4H9N, we're going to go ahead and convert that. We're going to add 1 carbon and 1 hydrogen because I've got 1 nitrogen involved. So I'm going to calculate this as if it was C5H10. So now I can do 2 times 5 plus 2 equals 12. Subtract my actual and divide by 2. I'm going to have 1 degree of unsaturation to get me something of that formula to draw out. Okay. And then C5H11Br, we're going to add 1 H because I've got 1 bromine. So I've got C5H12. So 2 times 5 plus 2 equals 12. Minus 12 divided by 2 equals 0. Okay, so if I was to draw out these possible structures, I would be wanting to draw something with this formula, right? Sorry, this formula in all cases, but we know how many pi bonds, we know how many rings to include. So for C6H8O, we could start off with a 6-membered ring. We could put a ketone in there and then throw in another double bond, right? And so then you can do it pretty quickly and say like, okay, I've got 1, 2, 4, 6, 8 hydrogens, 1 oxygen, all my 6 carbons are there. So it's way, way faster than trying to like draw stuff and then figure out what we have going on. So this is C4H9N. So I can just do 1 ring. Right, I've got 4 carbons here. We could also do something like that, where we have a pi bond instead. So 1, 2, 3, 4. Yep, we could do something like that. For C5H11Br, we could do something like that, where we've got 5 carbons and no degrees of unsaturation. Okay, so a lot of different options here. This is going to help you out when you're doing your NMR analysis in lab and your IR and stuff, because it's just going to allow you to know what shapes you should be drawing. Like, should you be putting in rings? Should you be looking for something like a carbonyl, right? So as always, let me know if you have any questions, and I will see you all later.